Alright, so let's take a look at double angle. So in our previous video, we discussed the idea of two angles being summed together or subtracted from each other, right? The sum difference formula. So if we wanted to find two of the same angle, right? So if you had sine of x plus x, right? We're saying that x equals y. In this case, we're applying the same sum difference formula. Then we'd only want the x plus x portion. X plus x is 2x, right? So to find a double angle, we are just going to manipulate this formula, or this identity, whatever you want to call this, and simplify it down. So first of all, we write it out, make x equal to y, get rid of all of the y's, right? We're going to substitute in. We also are only going to look at the positive portion, as noted earlier. We're trying to get two angles, not an angle of 0, right? X minus x will just be eliminated. And then we're going to simplify down, right? If we have sine x plus x, and that is going to equal sine x cosine x plus cosine x sine x. We can reorder those any way we want. So if we took that second cosine x sine x and reorder that as sine x cosine x, what we'd see is we actually have two sine x cosine x. And that is our first double angle formula. 2 sine x cosine x. For cosine of a double angle, we're going to do the same idea. We're going to take our angle sum difference formula for cosine, and we're going to manipulate it so that we're only looking at the addition portion of it. What we're going to find is there's actually 3 different options for how we define our end result, and they're useful for different reasons. But again, we're going to sub in x for every y, so we get the double angle. And in this case, you're going to get cosine x minus sine x sine x. That's the base one, right? That's going to be cosine squared minus sine squared. That's option 1. For option 2, and really option 3, what we're doing is we're completing a Pythagorean identity. So recall that if we have cosine squared plus sine squared, that equals 1. So if I added sine squared minus sine squared to the right side, right? Sine squared minus sine squared, that just equals 0. So that's fine that we did that operation. But now we're going to apply our identity. Cosine squared plus sine squared equals 1. And then we have 2 negative sine squared. So we're just going to say there's 1 minus 2 sine squared. For our third option, we're going to look for that Pythagorean identity, but this time we're going to try and wind up with a cosine squared instead of a sine squared on our right side of the equation. To do that, we need to have that negative sine squared and that negative cosine squared. And we'll see why in a second. So when we do this, until you get familiar with how this operates, keep using your sine squared plus cosine, or the cosine squared plus sine squared equals 1, and take a 1 out of both, right? We're factoring out that negative. So we have those 2 cosines squareds. So we're going to combine those on the left part of this. And then for the remainder, we have this negative sine squared x minus cosine squared x. Bring that negative out, and then put it in parentheses. We see that we've got our sine squared plus cosine squared. Make that 1. And then 1 times negative 1 is just negative 1. I realize that you guys will probably get to the point where you just see that happening, but until you're more comfortable, I suggest going through the steps. So those are your 3 options for cosine 2 theta. Just like we've done with other tangents, we're not going to reinvent the wheel. We're just going to take what we've already found, and we're going to put sine over the cosine. So we're going to take our 2 sine theta cosine theta and put it over 1 minus 2 sine squared theta, right? That's option 2. as the denominator, and then our sine double angle for the numerator. On the left side, sine over cosine, again, that's just tangent. Now on the right side here, we're going to make this into two ratios, right? That 2 sine theta cosine theta, that's the same thing as 2 sine theta cosine theta over 1. And the same goes for the denominator. When we get these tangent identities, what we're trying to do is we're trying to phrase these as tangent. Okay, so how do we get a tangent on the numerator? Well, we need to get that sine over a cosine. We can't just put a sine underneath that cosine that ends on the numerator, because that would actually be a cotangent. So instead, we're going to eliminate it. If we're going to eliminate the cosine and we need the sine to be over a cosine, what we're actually going to have is a cosine squared. So we're going to multiply the top and the bottom by 1 over cosine squared. On the top, that sine over cosine is going to become a tan, and that cosine over cosine is going to cancel, leaving us with 2 tan theta. On the bottom, now this is a little more complicated. That 1 minus 2 sine squared theta, that 1 we can rephrase as sine squared plus cosine squared. So we're going to plug that in, and then we're going to put that 1 over cosine squared theta across everything, right? Just like when we add or subtract with fractions and you need the same denominator, we can split by the same denominator. That's what we're going to do here. We're going to make each of those its own term. The sine squared, the cosine squared, and the 2 sine squared are each going to be their own terms all over that cosine squared. The first one, sine squared over cosine squared, that's just going to be tan squared, right? Sine over cosine. The second one is going to be cosine squared over cosine squared. That's just 1, right? The same in the numerator and the denominator cancel out and become 1. And then we have negative 2 sine squared over cosine squared. Again, sine squared over cosine squared, just tan squared. We keep that 2 in front. If we have a negative 2 tan squared and a tan squared, that becomes negative tan squared, right? We've got 1 positive 1 and 2 negatives, and nothing affects that plus 1. So we're going to wind up with 2 tan theta over 1 minus tan squared theta. And that will do it for our double angles.